you're listening remotely, we ask that you ask your questions in the WebEx chat, and then after each of the presentations, we'll stop and try to answer some of these questions. And so that's what we'll do for each presentation, as well as a question and answer session we have in the end. So I would also ask not to ask questions over your microphone if you're participating remotely, just because we have so many people, it'll just be hard to coordinate. For the folks in the room, I'd ask for you to use one of these microphones. Just raise your hand and I'll bring it around, not only so that the folks listening remotely can hear your question, but also because some of our presenters are remote, and so we want to make sure that everybody hears the questions here. So, okay, and with that, I will hand things off to IBM to start the first presentation.
Tools available on Summit and how to access them, and then talk about how to use those tools to distribute an existing model, go over some data handling information when distributing a deep learning model, go into how to launch those distributed deep learning jobs on Summit, and then go over some introductory best practices to practice when distributing a deep learning model on Summit. So getting started with some deep learning tools on Summit. So Watson Machine Learning CE is a software distribution provided by IBM, where we basically take all of these deep learning frameworks and tools related to their use, test them, compile them, and make sure they work well together, and then distribute them. This includes things like TensorFlow, Caffe, PyTorch, Horovod, and some other tools, useful tools that people working on distributed deep learning projects often use. On Summit, this package is available through the IBM WML CE module. So to use these packages on Summit, you use the module load command, the module load IBM WML CE. Loading this module will activate a Conda environment with all of Watson Machine Learning CE installed. So the user can use that directly. This module also sets up Conda channels pointing at the IBM public Conda channel, as well as an internal Summit-specific Conda channel, so that the user, if you'd like to, you can make a new environment. Say you're using tools that aren't available in the base Conda environment. You can either clone the base Conda environment or create a new Conda environment and cherry pick specifically the tools you want, and then add what you'd like to use on top of that. Now, the type of distributed deep learning that we're going to be focusing on today is data parallel distributed deep learning. That's the main type of distributed deep learning we've seen on Summit, and that's also the main type that we've focused on. Specifically, we'll be looking at the synchronous all-to-all data parallel distributed GPU deep learning. That's a mouthful. But basically, a process is created for each GPU in the cluster, and each of those processes maintain a complete copy of the model. Then, during training, the mini batch is spread across all those processes. So each iteration, the batch is spread across all of those processes. So each process is using different input data. And then after the forward pass, all of the processes compute their gradients, synchronize those gradients, and then update their local weights. So throughout training, all of the models on each GPU should remain identical. As long as they start with the same initial weights, they are all being updated with synchronized gradients, so they should always stay the same. So to look at this in a little bit bigger picture, so we take that data set, we split it up into separate local batches that we call the effective batch. So that's basically for each training iteration, that's the effective batch for that iteration. We feed those into the model, and then the models communicate their computed gradient to update their weights locally. So again, those models just remain identical throughout training. Now we'll start going through a little step-by-step how to actually modify a model to distribute it. So the main tool we use when performing data parallel distributed deep learning jobs is Horovod. So Horovod is a distributed deep learning framework with integrations into TensorFlow, Keras, and PyTorch, and is available in the WML-CE module. So Horovod really makes it easy to enable distributed deep learning within a model while providing good scaling across the entire cluster. So Horovod can use different communication libraries, including things like MPI, Nickel, IBM's DDL, and Glue. On Summit, it's built to use MPI, Nickel, and IBM DDL. So the main steps that are needed to distribute a job using Horovod are first to import and initialize Horovod, and then second step is to pin the process to the correct GPU. Again, remember there's a process per GPU, so we have to pin to the right GPU. We scale the learning rate and modify some hyperparameters due to changes in things like batch size from scaling. We add the Horovod optimizer, broadcast the global variables, so again, all the models start the same, and then modify the scripts to only do certain things on rank 0. And we'll go into each of these in a little more detail. So the first step, again, is to import and initialize Horovod. So you can see here, it's pretty straightforward. In Horovod and PyTorch, there's different libraries to import. But once you import those libraries, it's the same. So you horovod.init, and that'll initialize both the Horovod communicators and things like MPI. It'll initialize MPI into the covers for you, things like that. The next step is to pin the GPU the process will be running on. So in TensorFlow, you use the config proto to set up the visible devices. And here you see we're using the horovod.localRank function. So that'll be, in Summit's case, that'll be 0 through 5 for each rank on the local node, so one for each GPU. So here we'll pin, rank 0, so the first process on the node to GPU 0, the first GPU on the node, and so in the second process to GPU 1, the third process to GPU 2. In PyTorch, you use the CUDA set device function, but again, use the same horovod.localRank. All right. Another thing that needs to be handled when scaling a distributed deep learning job is the modification of hyperparameters. The only one we're going to talk about here is the learning rate. Later, Junchi may talk about some other hyperparameters. But the first one that you usually always have to modify is the learning rate. So as the batch size goes up, as it will in this case, we have the batch size is basically being multiplied by the number of learners. So as that goes up, we need to scale the learning rate to offset the effect of this larger global batch size. So we can use the Horovod function, horovod.size, to get the total number of learners and use that to multiply the learning rate. So that works well for initial scaling, so small scaling. Once you get into hundreds or thousands of GPUs, this doesn't tend to work well. So you may have to get into other methods and look at maybe just tweaking the learning rate, retuning the learning rate, and not just blindly scaling it by the number of learners. But that becomes pretty model dependent on larger scale. The next step is to add the Horvath optimizer. So in both of these cases, both PyTorch and TensorFlow, you basically just wrap your current optimizer in the Horvath distributed optimizer. And you can see the two methods, TensorFlow and PyTorch here. And so what that does is that's how Horvath actually handles the communication. So Horvath will use the native optimizer, the one that you pass it, to do the computations, and then will, on top of that, synchronize the gradient. And the next step is to broadcast the global variables. So again, we want, in data parallel distributed deep learning, we want to be sure that each model is the same throughout training. So part of that is to make sure that each model starts out the same. So we want to be sure that we broadcast the initial global variables so that all the models start the same. So here we see in TensorFlow, we use the broadcast global variables hook. We add that to our list of hooks if we're using any others. And in PyTorch, we just call the Horvath broadcast parameters function. So in both these cases, that will ensure that the model starts out the same, so that it can remain the same through training. The next step is to restrict, or I guess the last step is to restrict certain operations to happen on rank 0. The most important one here is checkpointing. So since we have multiple processes running per node, the first error we see a lot is that we have file access errors because all processes are trying to write the same checkpoint. So it's important that you restrict the checkpointing only to rank 0. If it happens to be that you want a checkpoint on each node, or you're writing to the local file system, maybe you only want a checkpoint on each local rank 0. But either way, you don't want multiple processes trying to checkpoint on each node. And there are other things that you'll want to restrict to rank 0. In TF-Keras, a lot of times you set verbosity to false, or set verbosity to false on everything except rank 0. That way, you see cleaner output and things like that. There could also be some data preparation or data ingestion operations that you only want to happen on a single rank, maybe single rank per node. So things like that, you'll want to be sure that you restrict to the correct rank. Right. The next thing we're going to look at, so those are all the basic steps you need to distribute a Horvath job, those 6 steps. Now we're going to look at a little more in-depth stuff, starting with data handling. So I've said it a couple times, but to gain any benefit from distributed training, each model needs to look at different data. If they all look at the same sets of data, then you're basically just multiplying your work by the number of GPUs and not learning anything new. So it's important that each learner is looking at a different sets of data. So there's 2 common approaches to handling this. One is data splitting, the other is data sampling. And an interesting point here is if the model is already randomly shuffling and sampling its data set, so if on a single non-distributed method you're shuffling your data set and sampling your batches from it each time, then it may be that you don't even have to make any changes to distribute the training. But in the case you're not, these are the kinds of changes that you'll want to make. So the first one we're going to look at is data splitting. So to make sure that each node is looking at different sets of data, you could split your entire data set so that each one gets different sets of data. So you can do this offline before training, so that maybe the split's the same each time, or if you want to put some more thought into the split, you can do this beforehand and then load up the data, store it and load it with respect to the rank. So you store it with the rank in the file name and then load it using horvad.rank. So that's one option. And another option is to split it at runtime, where you actually take the data, split it into chunks equal to the size, so horvad.size, and then index it based on the rank. And here, you be sure you split, both your actual data and your labels. It's also something to point out here, if your model uses batch normalization, which a lot of models do these days, it's important that each data split has the same distribution as the full data set. So that basically boils down to just, you want to randomly sample your data set and not just, index, the first chunk goes to node 1, the second chunk goes to node 2, unless, again, it's shuffled. Because it's batch normalization, if each batch is drastically different, each one is going to normalize to their local batch, and that won't really match the overall normalization. All right. The other way to split up your data, or to make sure each learner sees different data, is data sampling. So instead of actually splitting your data, you could shuffle and randomly select from your data set each time. And with a large enough data set and enough batches, then you're kind of guaranteed to get different data sets, different batches on each learner. So this works well if the batch size is significantly smaller than the overall data set. Again, kind of guaranteeing that you're getting different data on each node. And one important thing about this method is that you want to be sure that you use unique seed on each rank. Otherwise, you're doing the same data shuffling and using the same data on each node anyway. So you'll want, or you could be, depending on the timestamp on the node. So you'll want to be sure that you base your seed off of your rank, so that it's kind of guaranteed to be different on each node. And here you see that we're getting a random sample and using that sample to select from the training data and the training labels. And again, be sure that when you're doing that, those match up. You don't want to have the wrong labels for the sample. All right. And now, once you've modified your script, once you've handled your data, the next step is launching the jobs. In WML-CE, we provide a tool called DDL Run, which really it's there to facilitate the launching of these jobs. And there's specific hooks, specific functionality in there for Summit. Specifically, DDL Run will interface with LSF to get information about the cluster, and then use that information to launch the job across all nodes in your current reservation. And it does some useful things for you, like activating the current active Conda environment on all compute nodes. So it takes that little step further. Things like, so JS Run already on Summit, it will mirror the environment variable, so it'll mirror your environment across all the nodes. But there are some Conda packages out there that do a little more than setting up environment variables. So it's often important to have the Conda activation happen on each node. And that's one of the things DDL Run will do for you. So here in this example, we have an example of an interactive session where we run on 2 nodes. You see there we're doing the module load IBM WML-CE. So that loads up the module, puts us in the base Conda environment. And then once we're there, we can just DDL run the synthetic PyTorch example. So that, and then we see here the output. So the DDL Run tool will actually show the full output of the full command used to launch the job. And for more advanced users or users who want to go out and do something more interesting, can take that command and tweak it to do what they'd like. And that's the main reason we provide the output of that command. All right. So next, I'm going to look at some initial best practices. I know Junchi is going to get into some more, get deeper into some of these areas and go over some more complex kind of optimizations and best practices when scaling. But these, I want to go over a couple initial ones. The first one being staging to NVMe. So when ingesting data over the shared drive, you really see a negative performance impact over using the local NVMe drive. So this is something that when starting to distribute your job that you'll want to do. So here in this bsub script, you see I'm loading the data to the NVMe and then launching the job using that data. So the important things here are the bsub flag to get access to the NVMe drives is this -alloc flags NVMe. And then once you have that in your bsub arguments, you get access to the /mount/bb /user folder, and that's actually on the NVMe drive. So here you see an example using DDL run to copy data from the GPFS to the NVMe. It's important, or maybe when doing that, to use --accelerators 1. So you're basically saying you want one process per node to copy this data. It could be that maybe you want different, if you do have different data sets per node or something like that, that may not be necessary. But here we see using a single process per node to copy the data to the local node's NVMe drive. And then in the training job, the execution of the Python script, we see using that NVMe drive, the /mount/bb. The next best practice to recommend is the metric average callback. So a lot of models will use things like early stopping or synchronized or learning rate schedules based on velocity and things like that. But with Horovod, by default, only the gradients and by extension the weights are synchronized between processes, but not the metrics. So things like the validation loss, and if you end up adding any custom metrics, things like that aren't synchronized between the nodes. So it's important to make sure they are. So with TF-Keras, you can use the callback called the metric average callback, which will synchronize those basically all metrics. You'll want to be sure that you put this before any in the callback list, before any callback that might be using those metrics. So things like the learning rate schedule callback or the early stopping callback, things like that. You'll want to be sure that you've averaged the callbacks before then. In other frameworks, it may be necessary to directly average these callbacks, so make direct calls to Horovod Allreduce and things like that. So not all frameworks have such a clean hook to that. All right. And the last best practice I'd like to talk about is on-the-fly validation. So a lot of models, especially written in Keras, do on-the-fly validation, so that as they're training, they validate against a test data set, a non-trained data set, and show and make decisions based on that validation data set. If you don't also distribute that validation, that'll quickly become the bottleneck of training. So in TF-Keras, it's pretty easy to accomplish this by just splitting the validation data set or sampling it in the same way that you're handling your training data, and then using the metric average callback. Because as long as that validation loss is a metric, it'll be averaged with that metric average callback. In other frameworks, you might have to, again, make direct calls to Horovod Allreduce and things like that. But you'll want to be sure to split that validation data the same way that you're splitting the training data to, again, make sure that on-the-fly validation doesn't become a bottleneck, because it does quickly. As your training gets faster, your validation will start to stand out. All right. And that's all I had for today. We can go ahead and do some questions. If I don't know if we want to, I don't know how we want to do that. I'll let Tom speak up and handle it from here.
Okay, thanks, Brad. Does anyone here in the room have any questions for Brad at this point? All right, looks like Wayne has a question. I'll let him ask.
How many
Can I
rows?
ask a
How many
question?
Summit nodes will this run up to?
So
Yeah, so it's supported on 950.
954.
Yeah. So you can get started using on that many nodes.
The underlying tools will work on more than that, but currently that's what's being supported on Summit.
Another question. Do you have like the director of complete examples for different cases?
So there are examples provided in our tool set. Most of them are kind of basic examples. There's also some examples in Horovod's GitHub repository if you're interested in some more complicated ones using Horovod.
Yeah, so the Horovod GitHub is a good place to start after looking at the documentation.
Okay, so I see there's a question also in the WebEx chat. Says if a GPU on one node needs to communicate with a GPU on another node, does the communication go through the CPU GPU bus?
Okay, so the underlying communication is done through Nickel. So I think maybe we should wait till the next presentation to discuss that further.
Okay, if it's not answered, I will follow up again with the QA session.
May I ask a question about WML? Proper can hear me?
Yeah.
What's the release cadence? What expected release cadence for WML-CE? Because what's right now on Summit is pretty old, right? It's TensorFlow 1.15, and already there is TensorFlow 2.1. It would be great to know what to expect from the update of this module on Summit.
Right. So we put out a product around once a quarter. So there'll be a new one coming out in another about 2 weeks that will have TensorFlow 2.1 in it.
That's great to know.
Yeah, and also the WML-CE does provide an early access conda channel that gives access to the newer frameworks that maybe aren't fully supported yet. But if you're in a situation where you need that newer framework or that newer functionality, there is an early access channel. And if you just, we can make the information on that available. But again, those won't be supported frameworks, but they'll just be pre-release early access. And if you need that functionality, you can add that to your Conda RCP and get access to those channels or to those packages.
That would be great to know. And also, is there any relations between machine learning stacks that are provided by IBM in Docker containers and Conda channel?
Yes, the Docker containers that we provide are packages. All the packages inside those containers come from the Conda channel, so that they should be identical. Really.
Okay, thank you.
Just different forms of using them.
So I see there's another question, let's see here in the WebEx chat. So at times, while CF user support may not be conversant with IBM Machine Learning Toolkit entirely, in such case, is there an IBM contact person to whom a user can contact directly? I think the proper channel there is to contact user support, and we can contact those IBM folks, unless Brad or Bryant say otherwise.
No, I think that's right.
That's the case, yeah. And once that comes over, we are the second step for support in this case. So, the Oak Ridge support will contact us, either Brad or myself directly in this case.
Okay. Then there was a question there that looks like it's for me. Yes, these presentations will be made available after the webinar. And then a little while later, I'll put the recording up as well, so that if you wanted to come back and watch again later or pass this on to a colleague, you can do that. So are there any other questions? Yep, looks like we have one more in the room. Let me take the mic back there.
Yeah, I guess this is a question for OLCF. For those of us who don't have a project approved on Summit, I know there's another system that has the same architecture as Summit, Ascent. Is there a way we can try that, this presentation that Brian had for us on Ascent, and what would be the procedure to get access there?
So the Ascent system is really specifically for training events that we schedule, not for sort of follow-up. So there's not really a channel there to be able to run. It's possible, though, in the future that we could hold events that, where you do have access to either Summit through training tokens or Ascent to be able to test some of these things out.
Okay, thanks.
And that is something I can add, maybe not directly related, but these packages are also available outside of Summit, so you can use the public IBM Conda channel, and they basically work the same way. The distributed packages may not have support for as large nodes, but off Summit you probably shouldn't need that. But so you could get started there if you're waiting on approval or things like that, and work on your model using the same versioning and same packages that you'll be using on Summit. And those same packages work on x86 as well.
Can you repeat where's the place where I can get started? Thank you.
Yeah. So the public Conda channel, and we can make.
I'll put that in the WebEx chat. I'll give you some documentation.
Yeah, and we'll make sure that documentation for the public channel and the early access channel are available after the call as well.
Thanks.
Hi. So for workflows that will require additional software packages, how easy is it to build on top of this? For example, if I wanted to add Apache Spark on top of the builds that you have, would that be an easy thing to do, or have you tried this? How do we go about doing that?
You should be able to install PySpark into a Conda environment. So you would want to clone the environment that's in the WML CE module into either your home directory or into GPFS, and then from there you can install PySpark. Once you've set up Spark, and there's a lot of different things you can do there. I believe there's some TensorFlow and Spark support, and also PyTorch and Spark support.
But yeah, as far as how hard it is to set up your own environment with tools that aren't provided in the module or the Conda environment, it should be as simple as either cloning the environment or making a new one and just installing the specific packages you want. We do, and on the Oak Ridge Summit user guide, we do have a little step-by-step example of doing that.
Thank you.
I'll put a link to that also in the WebEx chat for anybody else that's interested in seeing that. Just have a quick link to it. Okay, so do we have any other questions for Brad and Bryant at the moment? Let me check WebEx here. Okay, so I see one. It says, how do you determine how many nodes we can use? Does data is it automatically parallelized over nodes?
So for the most part, your scripts will probably use a function called hvd.size, which is going to tell you how many processes there are. And in general, you want that to be the same number of GPUs. So if you ran on 4 nodes and there's 6 GPUs on each one of them, then that hvd.size is going to return 24. And your scripts can be modified if there's any cases where you need to know how many processes there are. That's what you would use. As far as the DDL run tool, that will use information from your B sub job that you submitted. So the way to choose how many nodes you're going to use is when you create your B sub job, you specify it. So on this slide, you can see that top line is specifying how many nodes you want to use, and it's going to use all the GPUs on each node.
Okay. Are there any other questions before we transition to our next presentation? Okay, if you do have additional questions that pop in there while we're watching these, or that you didn't ask, we will have a Q&A session at the end too that you can ask additional questions for any of the presenters. So thank you for the presentation, Brad and Bryant. We will transition over. Let's see if we have Sylvain. We didn't check your connection earlier. Can you verify whether or not we can hear your audio? So I see Sylvain is connected. I don't see an audio connection for you, though. Let me try to chat with him real quick and figure this out. If you stay tuned just a moment.
All right, can you hear me?
Yes.
Yes, I can hear you now.
Oh, you can. Okay. Okay, that's perfect. Sorry,
Thank you.
somehow I was muted. I just couldn't talk. So do you see my screen?
Yep, we see your screen now. Looks like it's all set. There was a specific name that was different from your Colin name there that needed to be unmuted.
Yeah, there is some WebEx magic happening there. I'm not sure what exactly it is, but whatever, it's working. Sorry about that. So I'm Sylvain. I've been working on Nickel for since the beginning, pretty much in 2015. So it will soon be 5 years now. And the goal of Nickel is to really help deep learning going parallel and using multiple GPUs. And so we started that effort a few years ago, like 5 years ago, trying to improve the situation of communication in deep learning frameworks. And since then, it has evolved quite a bit. So I'll go through all of that. So the goal of Nickel is to provide an optimized inter-GPU communication library for deep learning first, but we're expanding that to pretty much all the use cases. And the goal here is to really use at its best technologies like PCI, shared memory, NVLink, sockets, InfiniBand cards, or any network really. So anything we have, and make sure we get the best performance out of all of that. So there are different ways you can get Nickel. We provide binaries, including binaries for power. I'm not sure how those are actually deployed or integrated in other products, but we have that way. The other way is the source code. We actually are open source. There's a GitHub project with all the source code in there, and it should be fairly easy to recompile. Basically, just type make, and that should work. Other than that, we also have performance tests that are quite important if you want to make sure your setup is correct and you're getting the performance you should be getting. And those performance tests are also open source and available on GitHub. They are on a separate project though, because they're kind of, also we used to not be always open source, so that has been historically a separate project. So Nickel's goal is really to use the best hardware, I mean all the hardware you have, and really make sure you get the full performance out of it without having to do anything. That's really the goal here, to not have everyone have to figure out what they have and whether they should do one communication pattern or the other, and try to take all of that on our side and make sure everything just runs out of the box with no effort. And the performance you should get is actually very dependent on the hardware you have. For example, if you are just within GPUs within a system, depending on whether you have your GPUs are connected through a slow CPU link or through a PCI Express switch, you'll get between 6 and 12 gigabytes per second. On a Summit node, you can get up to 40 or even more than that if you're just running between GPUs that are NVLink connected, not on the full system. And then if you go on platforms that are even more targeted at deep learning, like DGX system, you can go up to 60 or 130 gigabytes per second. Similarly, internode, depending on your network technology, you'll be bottlenecked by that. And you can see there is a wide range of performance between very common systems with 10 gigi or 100 gigi systems, down to DGX systems that have a very bandwidth-heavy configuration with a lot of NICs. And in the middle, Summit is kind of a balanced HPC system, which has something that's definitely superior to any system you can find. Not quite as fast as the DGX system, but that's not the same scale either. So this is pretty much what you should get, and the goal here is that you don't have to worry about how we get that. Now I'll still go into details and explain how what we do to actually achieve this kind of performance. But before that, I'll quickly go over as to how we integrate into the deep neural network training. Even if actually that has been just explained before, so I go quite fast here. So as it was mentioned before, we want to train our own database of data, even multiple times. And so we batch the input, we go forward, backward, we kind of compute how wrong we are and how bad we are at doing our recognition. And we basically compute the error. And then we come up with gradients, and using those gradients, we update our parameters, which is basically how we learn, and we continue again until we no longer learn anything, and we consider we have learned it enough. And how we go from one GPU to multiple is pretty easy, as it was mentioned. We just split the batch into multiple mini batches, or we have mini batches that we split even more. And each GPU or each rank will basically compute its own local error. But before we learn, we actually do that important step, which is the all reduce operation, which is just summing the gradients across all the GPUs, so that all the GPUs have the error from the others as well, coming from the other input, so other images or other samples, so that they can all learn from the whole batch and not just the sub part of the batch that they had locally. And then everyone has all the gradients, so they can all learn in the same manner and update the parameters in the same way. And so Nickel is right in the middle here, and its performance is important because if you want to scale, you want to make sure that the time it takes to communicate will always be small compared to the time it takes to compute. And so that's per GPU time to process the batch should be larger than the time it takes to do the Nickel reuse. And that's why performance is critical, because the smaller the communication time is, the more you can scale, and because you can use smaller batch per GPU. Otherwise, if your communication time is too large, you will need extremely large batch sizes to still scale. And we know that having too large batch sizes might affect the accuracy and the rate you learn, or even if you learn at all. So depending on the model, you can scale more or less. There are some models that can get up to 32,000 batch size. So those are fairly easy to scale to large number of GPUs. Some others can't go beyond 2K. So you'll be quickly limited in the number of GPUs you can use. As far as integration goes, well, Nickel is just a library just like others, and it's used by frameworks or by module like Horovod inside frameworks that will use it for you, and you should not have to worry about it. Just need to make sure it's there, and the framework has been compiled with it, but usually everything is already coming with all integrated. So hopefully that's not something that users should have to worry about. Yeah, it's just a library like the others. Of course, if you're not running on more than one GPU, you might not need it, so that's why you might not have been exposed to it. But on all clusters, it should be there, and it should be working. The Nickel user interface now. So this is pretty much the whole picture of the Nickel API. So it's actually quite small to cover something like MPI-1. It's not obviously the whole MPI-1 set, but this is kind of where we're going. Even if we won't actually cover everything that is in MPI-1, we want to kind of match the functionality we have in MPI-1. Right now, everything that's present are the things in black. The parts in gray are not there yet, but they're hopefully be coming soon. And so we can see that basically what we have is a few things to create communicators, which is basically create a group of GPUs we want to perform communication on, and then destroy it, same thing. And then we have the collective communication, which revolves around all reduce, because of course, deep learning applications have been focused on that so far. And so we have all reduce, of course, we have broadcast and reduce, because those two combined make an all reduce if you want to split the two phases. And also reduce scatter and all gather, which also can be combined into an all reduce if you want to split things differently. And then finally, we have the aggregation composition calls, which are group start, group end, and which are a powerful tool to compose things together, and that's how we intend to actually implement all the point-to-point operations. But I'll talk about that later in the next slide, or maybe at the end. And so yeah, so send receive are coming hopefully this year. So if you're interested in that, to create new models or to do new things with it, or even as an HPC user, if there are HPC users who want to give it a try, stay tuned, because we'll try to get a preview fairly soon so that people can try it and tell us what they think about it. One last thing I didn't mention is the fault tolerance. So this is something that we've been trying to add, and this is basically relying on the get async error and abort functions, where we can, if there's an error in the middle of a job, we want to be able to abort the communication, so basically stop what was happening, and then we can recreate a new group, maybe with less ranks, less GPUs, or more. We could also try to grow it, and then continue communication based on that. So we're not assuming, like MPI, that if something goes wrong, we have to tear down everything, and we're trying to get something that actually let us recover, recreate a new group, and continue without stopping. Now, if you have, like most deep learning frameworks, some checkpointing in it, it's no big deal. You can actually stop and restart. But sometimes it still takes a long time to restart a job. So that's something we're trying to work on. And some frameworks like PyTorch are actually actively trying to achieve that. Another thing about usage, so right now, a nickel communicator, in a communicator, one nickel rank is one GPU. And that's a nickel communicator handle. That's a pointer you get. And you can actually manage one GPU with that object. And there is no assumption about how you launch things. If you're launching one process per GPU, if you have a single process managing multiple GPUs with multiple threads, or even with a single thread, there's no problem. Everything is supported. And that's because we just manipulate those handles, and one process can have multiple of those if it wants to manage multiple GPUs. That's quite a difference with MPI, which usually the MPI model is to use one process per GPU, which we support, of course. It's just that we're not limited by that. You can have one process per node. You can decide to have one process per socket. That's things that people do, and it's supposed to work. And our model enabled that. However, one thing that MPI users might find as a constraint is that it's not encouraged to create multiple nickel communicators. Because nickel is running on the GPU, to process CUDA buffers more efficiently, we also have the constraints that come with CUDA, and there is no guaranteed concurrent progress of CUDA kernels. So if you launch two nickel operations on two completely separate communicators, you might end up with a deadlock if one is blocking the other on one GPU and it's the reverse on another GPU. So I explained things about nickel com split at the end of the presentation. So a little bit of explanation of how it works inside Nickel. So hopefully that's something that you should not have to worry about. But just to explain how much we do to try to actually not have users worry about things like hardware topology and how to do things efficiently, I explain a little bit how Nickel works. So Nickel is running a CUDA kernel inside on the GPU, and that CUDA kernel is handling a continuous stream of data that is coming from previous GPUs in the ring or in a tree. We have different way to communicate, and it can reduce that data with some local buffer it has to perform the final or reduce. It can then store the result to the local buffer as well and send it to one or multiple GPUs. And so that kernel is running on the GPU, and it's constantly getting data in, pushing data out. So we try to pipeline things very efficiently. so that data is always flowing in all the direction and using all the links we can. And if we need to go between different nodes, we can actually push data through a FIFO in memory, and then a CPU thread will actually make sure to push data to the next node in another FIFO on the remote node that the next GPU will read from, and then data will continue to flow that way. Now, if you have GPU direct RDMA, for example, if you have an InfiniBand NIC, you'll be able to even directly read from the GPU and send to the next machine directly to the next GPU memory. And that way you can completely bypass the CPU memory. And even if the CPU thread is still initiating the transfer, it's not actually, I mean, data is really going just from the GPU to the NIC and from the NIC to the GPU. Now, a big part of Nickel is to actually do the right thing on all the potential topologies we can be exposed to. And there are many types of topologies. You can have a PCI standard x86 system where you have a few CPUs, a few PCI switches, and a NIC. You can have something like a DGX1, which has a cube mesh NVLink topology between the GPUs, and then multiple NICs we want to all use together. We can have DGX2, or we even have an NV switch, yet another topology, and then we can also have P9 systems with different NVLink configurations, which we all want to use at their best, with that nice NIC in the middle that has actually two PCI legs, but still share the same IB ports. So all of that is making the topology detection quite critical, because if you don't get it right, you will have multiple flows using the same links and things will not be balanced, and you'll end up with something that's suboptimal. And of course, we support many more than that. We have support for ARM coming, Intel, AMD, single root complex, dual root complex, pretty much everything that's possible. And so Nickel actually has a fairly extensive topology detection system, including NVLink, even NVLink between CPUs and GPUs, to make sure we use them the best way we can. And then we have a multipath search system that tries to find as many paths as we can within the node, so that we can actually aggregate the bandwidth on all of those paths to use all the paths in the system in the most efficient manner. And so if you look at a P9 system at the bottom, you'll see that we make sure we have one flow that uses one IB link, and another flow that uses another one, and also using local transfer as much as possible, and also using NVLinks and the inter-CPU bus, but not too much, just in the best way we can. And that can only be possible, that this is only doable if you have a very precise description of the node. And this is what we build inside Nickel. We build that topology graph, and then we have a search inside that. And so you can see here how, depending on what you have, you'll have 1, 2, or 4, or 8, or 8 flows, all running at around 100 gigabit per second, and giving you an aggregate bandwidth that can vary from 12 to 85 gigabytes per second. And that's a very big part of Nickel. Now, we also have a few algorithms and protocols that we can use within Nickel. We try to minimize them as much as we can to just keep things as simple as we can, but we still needed to have a few. And so for GPUs communicating to each other, right now we have 3, which are L128 and Simple. LL staying for low latency. They're really optimized for the latency, as you can see, having up to 6x better latency than the Simple protocol. But then it comes at a cost of bandwidth as well. And finally, the Simple protocol has hold the bandwidth, but has pretty high latency. So we should automatically switch from one to the other in Nickel at the right moment. But all have their advantage, and depending if you're more focused on latency or bandwidth, they should actually kick in at the right moment. Also, as how we communicate in the all-reduce algorithm, we have right now two main algorithms. Ring was the initial one. It has all the bandwidth you want, but the latency tends to be linear with the number of GPUs. So if you want to scale to very large numbers, it won't actually work really well. And that's how tree come handy, because they have a logarithmic latency. So it scales much, much better. And the bandwidth is fairly close to the full bandwidth as well. And actually, yeah, in previous presentation, I've seen some environment variables that were disabling trees in LL. Hopefully that should not be needed. I'm not exactly sure why, but that's something that we usually discourage users from doing, because that's something that should already be optimized. And if there is something you need to disable, then we need to fix that. As to why we did trees, so these are numbers on Summit on the whole cluster. So if you were wondering how far you can go, you can pretty much everything, provided you have the credits. And you can see that the ring's latency is linear. So as you go to lots of GPUs, you will end up taking up to 50 milliseconds, even just to do no reduce on 8 bytes. Which is kind of a shame. And so that's how trees come handy, because they're logarithmic. And also it improved the bandwidth as a side effect, because you can achieve much better efficiency, even on something relatively small, like 64 megabytes. So this is not getting full bandwidth because 64 megabytes is very small, but this is something that's fairly efficient, especially compared to rings. However, and also that's why you do not want to disable trees if you want to scale. But we're not exactly at 24 here, and there are a few reasons for that. First, as I mentioned, is because it's 64 megabytes is fairly small for such a big number of GPUs. But also we've been working on adaptive routing recently, and we're hoping that with adaptive routing enabled, we'll be much closer to the 24 gigabytes per second that we should get. So future, and actually quite near future now, we continue to improve performance, of course, and that's been continuous for a few years now. And there are a few things coming in Nickel 2.6 that should be there in a few months. And one of them is adaptive routing, as I mentioned. So you might need to set something on Summit. The IB service level, so Nickel IB SL might need to be set. That's something we need to see. But hopefully that will actually improve performance significantly, because you should no longer be dependent on how much load there is on the network if you enable adaptive routing. Because even if there is a link that's contended, hopefully Nickel IB will actually use another link that should be free. Which was not the case so far. It was static, and so if you were not lucky, you would get poor performance. If you were lucky, you could get better performance. So basically, what you should see is the performance going from 2.4 to 2.6 here. That's something you should experience with 2.6 with adaptive routing on Summit. The next step is going with Sharp, but that's not something that's available on Summit. Summit only has Sharp v1. But if you have the opportunity to run on clusters with the next generation of Mellanox cards with CX6 and the new switches, you might be able to use Sharp, and that would give you an extra boost in bandwidth. And so that's all coming in 2.6, which has a preview available already on GitHub, and yeah, you can give it a try. After that, we've been working on a few things, and the next steps are CumSplit and point-to-point. So CumSplit, the goal of CumSplit is to really make the right decision and to enable multiple communicators. This has been done by some for some time now to do things like hierarchical collectives. If they want to communicate intranode and then internode, but they don't want to always communicate with the whole set of GPUs. And also model parallelism in the case where your model being split between different GPUs, they don't have to all communicate with each other, just with the same GPUs that have the same part of the model. And this is something that is important in Nickel because we have this extensive topology detection. being able to know that we do not want just to create a smaller communicator, but we want to create multiple of those. We can make sure that when they operate together, they can operate at full speed in the most effective manner. And the example that is shown here is pretty clear in the sense that if we are just seeing the communicator as the black communicator, the black group or the green group, we might actually make decisions that would be suboptimal because we might want to use both sides to get not 12 but 24 gigabytes per second. But that would actually mean we would need to cross the inter-CPU link. And if the other group is doing the same, we'll have that inter-CPU link that will be extensively used for no good reason, because if you keep things local, you will get the full bandwidth using the two at the same time, and with the minimum amount of data going back and forth for no good reason. The other advantage of doing that is to share the resources between the different groups. So even between the case on the right and the case on the left, we will be using the same communication, same resources, same FIFOs, so same memory regions. The same resources, if you're using Sharp, for example, you might be limited in terms of resources. So you might want to have all your communicators be able to use them, not just one. And finally, to avoid deadlocks, that can be helpful to also have everything share resources, because then Nickel can actually detect that you're doing something wrong, or can enforce some ordering, which is not the case if you create two completely independent Nickel communicators that do not know each other. And finally, the other feature we want to provide in a fairly short time frame is point-to-point communication. I know it's something that we've been talking about for a few years now, but hopefully now it will be coming soon. And it's just about adding Nickel send and Nickel receive. And using Nickel group start, group end, you can combine those or fuse them to express any point-to-point like operation you want, including scatter, gather, all to all, or to all V, or to all W, neighbor collectives, everything. And all that with just two functions. And then it's up to users to just express that. But it should actually not be much more complicated than just calling all to all or scatter or gather. It's just a few lines of code. And that's pretty much it for my presentation. As a summary, we're trying to optimize everything on all platforms and try to get that out of the user's way, because it's a really complex subject, and everyone trying to reinvent it is usually not the best way to do it. So we're trying to get that done for them. And we want to optimize that on all platforms, so that if you're running on your local laptop, or if you're running on a 24,000 cluster, it should be the exact same experience, at least as far as Nickel is concerned. And we only rely on CUDA. We can work perfectly with MPI. You still need something to launch the processes, manage them, or even some CPU side communication. We're only handling the GPU side communication. So it combines really well with MPI as the CPU side communication side. But things like PyTorch, for example, they have their own launcher. You can also work with PyTorch with Nickel, and you don't even have MPI in the picture. If you're using Horovod, you will have MPI in the picture, because Horovod is basically MPI plus Nickel plus some deep learning oriented services. But yeah, any environment works. And again, where you can find the bits, although hopefully it should always be available on your cluster. And that's it. Any questions?
Can I ask a question? What is the reason for trying to replicate MPI one-sided capabilities?
So we're not trying to have MPI so MPI one-sided is weird to me, because MPI to me doesn't have one-sided. It's MPI 2. MPI 1, or are you talking
My
about
mistake.
MPI
I meant point to point. I'm sorry. I'm driving.
Okay.
And
Sure.
I got distracted. Yes.
So it's for new usage is mostly. So first, HPC users, they've been asking for it for some time now, and that's something that they're all quite interested in. The other reason is new usages like model parallelism, and there are more and more asked for, even in deep learning, for being able to split data differently or to parallelize things differently. And to do that, usually it all goes down to doing send receive. So yeah,
the logic is that people would basically just use the MPI launcher and not have to do anything in terms of MPI. I'm just trying to understand the logic behind introducing something that's not part of a standard, but just part of an API that you define for people to put in their code.
Oh,
when there is a standard for point-to-point, that's the part. Are you offering better performance? Where's the catch, essentially?
Yes, so it really goes down to performance because we have double G detection here is extremely critical. I didn't show the numbers of basically nickel versus MPI, but in many cases it can be quite large. Now, there's another thing, because we are running on the GPU, having a CUDA kernel that runs on the GPU lets us do things that you couldn't do otherwise. But it also comes at a certain cost and some constraints, as I mentioned, about the multiple communicators. And so it's kind of a trade-off. And that's why nickel is better than MPI in some sense, but it's also more constraining in some others. And it's kind of also up to the user to know if it wants, for example, the reduce to execute on the CPU or on the GPU. If the GPU is the bottleneck, maybe actually it's faster to run on the CPU because the CPU is doing nothing. But if the CPU is the bottleneck, or if the GPU still has some space and you want to leverage that for your communication operations, then it might be more efficient to ask nickel to do it because, yeah, it's just faster that way. And also because the buffers are on the GPU. So in a way, we're trying to have something that's more explicit. The user can choose to do one. I mean, the application developer can choose to use the one that's the best for him. And the goal here is to be as simple as we can for users to change from one to the other. And that's why our API is quite close to the MPI API. So replacing MPI or reduce by nickel or reduce is fairly simple. But there are some differences that make them not, you cannot do MPI on top of nickel or nickel on top of MPI, said differently. And that's why it needs to be two separate things, but we're trying to stay as close as we can when it makes sense. Did I answer your question?
Almost. The only part that is still a bit unclear is about the point-to-point double two-sided performance, whether you're actually getting better performance for those. Those were the ones that surprised me. I mean, the fact that nickel would be a better option for collectives, that was well known. The part that came as a surprise is that you're introducing point-to-point that look like MPI, replace the functionality of MPI two-sided, and just add more things that are now not based on the standard. So are you getting significantly better performance than a CUDA-aware MPI implementation? For point-to-point, that's the question. And I'm sorry, I'm not going to ask anything else because I'm taking up everybody else's time. It just came to me as a very big surprise to see the point-to-point stuff.
So it's a very good question, though. So I try to be quick on that one. So that's something we need to see, of course. And when it's out, we'll be able to talk more about that. But yes, there are cases that we see should be faster because especially if you want to do something like an old tool, we will have better topology detection for NVLink usage in general. And also having everything local to GPU means if you have, for example, an NV switch system with all the GPUs have direct connection with NVLink, you can have a single kernel, do an old tool with all the other GPUs. If you were to use MPI, you would need to use CUDA memcopy operations. And so, for example, if you're doing an old tool with 16 GPUs, you would need to initiate 16 different operations, and the latency of that would be higher than if you start a single CUDA kernel doing all of that.
Thank you.
Okay, are there any questions here in the room for Sylvain? Okay, there are a couple here on in the WebEx chat that I see. So there's one here that says perhaps a Horvath plus nickel question. How do we identify and avoid a failing rank on a node? So fails at the nickel operations, for example, all reduce. Is there a way, recommended way to identify and avoid that, Sylvain?
So fault tolerance is something that HPC folks have trying to achieve for the last 20 years without success. So we're trying again, in a way. And we're kind of learning also as we go. We have basic difference with MPI is that we don't have a COM word. So we are creating communicator. We can destroy that communicator and create a new one. And so this is something that we've seen Chainer. So Chainer has actually started using that, but then Chainer moved to PyTorch. And PyTorch is also trying to really provide fault tolerance. And this is something that the frameworks has to do. It's not, Nickel can only provide the API, but that's only part of the job. The hard part is to have the layer above it detect the error, report it in a consistent manner, and then shrink or extend the communicator, recreate a new communicator, and continue from there. Horvath being MPI based, I would assume that Horvath would have a hard time doing it, because even if the Nickel side could support it, the MPI side won't. So I would imagine it won't be easy. But even in PyTorch, it's still work in progress, and that's something we are still, there are things we're still learning. So hopefully we'll get to it. And hopefully maybe we can even then, how to say that, give some recipes, and maybe for MPI to improve and provide that as well. But that's very much a work in progress, where it's not only Nickel, it's full stack, and MPI right now is not capable of that. Did I answer the question?
We'll have to, let's see. I think we'll have to wait here and see if they respond. But that was a chat question, so I don't have an answer to that right now.
Okay.
So there's a couple other questions. Let's see. Someone's asking about one of your earlier slides where you mentioned the COM split, and they were asking if you could elaborate a little more. They weren't certain if you were saying that using that is discouraged.
No, so actually creating so okay, let me go back to the API. So using Nickel Community Rank, which is the basic function for creating communicators, you could actually create multiple of those. And that is what is discouraged. And so far we're saying just create one, and that's it. But we want to enable users we want to enable them to create more than one if they really need to. And that's why we're adding Nickel Com Split to create multiple communicators in a more controlled manner. And that would be more efficient in all possible ways, resources, speed, everything. And also safer. So I'd say that up to 2.6, do not create multiple communicators. That's something, I mean, do it at your own risk, and we won't guarantee much. After that, if you're using Com Split, you'll be able to do that safely and hopefully have, or more safely, and have good performance as well.
Okay.
And the very basic example is this one. Is this one. If you're doing multiple Nickel Community Rank on the case on the right, we will not make the right decision because we won't know there is another communicator using the other side of the NIC. And that's why things might be suboptimal, might not work well, and you might have issues. And that's why we really want Nickel Com Split to be able to make the right decision and make sure everything can work together.
Okay. Okay, thanks, Sylvain. There's a couple more questions, but I think we might want to wait until the end to answer some of these other ones, just to continue on with our schedule. So, yeah, we'll get back to those at the end after Junqi's talk. So we'll go ahead and let Junchi steal control of the presenter mode there and let him take it away.
Okay, so hello everyone. My name is Junqi. I'm from Oak Ridge. I'm from Oak Ridge Distributed Computing Facility, Advanced Data and Workflow Group, and I would like to share some of experience and considerations in scaling deep learning applications on Summit. So first, I will give a quick overview about Summit and deep learning on Summit. Then I will try to work through end-to-end typical deep learning development cycle, starting from deployment, such as things about framework of choice, native or versus container mode, to parallelization, how to distribute your PyTorch and TensorFlow code, to performance tuning in terms of compute, I/O, and communication. Then once you code this tune and scale, then talk about a little bit about model tuning with hyperparameter search, and also a little bit on the model deployment. That's in terms of inferencing. But my main focus here will mostly about distributed deep learning and its performance tuning on Summit specifically. So a few words about Summit. Summit is ideal for deep learning because it has over 27,000 V100 GPUs, and thanks to Tensor Core, it can deliver about 3 exaflop in half precision. That's a tremendous amount of compute. And there are also, if you look at the per node architecture diagram, there are aggregately over 7 petabytes no local NVMe. And we'll talk about that later, why it's essential to keep up with the GPU processing speed. It has NVLink 2, not only between GPUs on the same socket, but also between GPUs and P9, and EDR InfiniBand cross node. All of this can deliver a high performance collective communication. You heard from previous talk, that is also essential to keep up to deliver a scalable deep learning on Summit. So people are already doing full Summit scale deep learning. Here I just list these examples. There are extra scale deep learning in climate science, in medical science, and in material science. Typical network is CNN type of network, also including a neural architecture search with Mendel. They all achieve about or above 1 exaflop in sustained performance. I was part of the material science project in which we achieved over 2 exaflop in peak performance. So this table shows the deep learning in terms of domain and the methods of use. Of course, this is a growing list. So if you don't find your project corresponding to one of the check marks, don't be alarmed. This is just to show you the general trend. So we characterize the projects in terms of supervised learning, unsupervised learning, reinforcement learning, and hyperparameter search. As you can see, most of the projects are using supervised learning. And within supervised learning, the convolutional neural network, CNN, is mostly heavily used, which should not be a surprise because it is, after all, a driving force for the deep learning success. So in the following slides, we mainly focus on the CNN type of architecture in terms of scaling deep learning on Summit. So also to give you some baselines for deep learning performance on Summit, Here we use the Core 2 deep learning benchmark. Core 2 basically is a set of benchmarks that was used and are used for machine procurement. So for the first time, there's a set of deep learning benchmark to measure the performance of deep learning applications across platform. The bar chart basically shows that the speed up using Titan as a baseline. Say if you're running deep learning application on Titan, what's the speed up you can get for different type of neural network architecture ranging from RNN to different kind of CNN type of workload. So because CNN type of workloads is generally more computational intensive, especially VGG type of network, you can get average about 60 times a speed up. And we also show a strong scaling of ResNet 50 on Summit, which is in terms of Keras. This is just to give you some baseline performance that you can expect on Summit. Now, let's work through the end-to-end typical deep learning development cycle to talk about something specific on Summit. Let's start with deployment. So the first step is to have a software environment and for your deep learning project. When we talk about MLDL software stack, we consider the programming interface, C++, Python, deployment environment, whether you run it natively or within a container, and framework choice. We do notice that users start converging to two framework, TensorFlow and PyTorch. Here, this pie chart is basically comparison between these two frameworks for ResNet 50, starting from 16 nodes up to 128 nodes on Summit. We consider, since we only care about the scaling performance, we consider two types of communication strategy. One is using Nico across all the ranks. The other is so-called hybrid, which means we use Nico within a node and MPI cross node. So in all the cases, the two frameworks deliver a comparable performance, with TensorFlow show a slightly advantage. I don't want to start a debate with which framework is better, but generally for CNN type of workload, we do see TensorFlow performs slightly better in this case. Another thing to consider is to whether to run your application natively or within a container. So as you know, most MLDL frameworks are based on shared library, such as Python or R. If you have run a shared library application on Titan, you must notice the pain because it can take hours to just load your application due to those shared libraries usually have a deep software tree, and the file transfers operations can stress out the metadata server. But the GPS file system on Summit sort of alleviate that. Here we consider two things for, the first thing is the impact of loading shared libraries on GPF on Summit. We do it from GPFS, from node local NVMe, and from within a container. So for the top right bar chart, it shows that for the blue bar is the loading, just loading TensorFlow from one node up to 1,000 node on Summit on GPFS. You see the continuous increase of loading time. And if you load your TensorFlow from the node local NVMe, the performance as indicated by the orange bar is a constant loading time. But of course, there's an overhead. You first need to stage or copy over your software stack to the node local NVMe because it's purged between jobs. So if you consider that, it's actually comparable with loading directly from GPFS. But if you load the shared TensorFlow from the Singularity container, which is available on, which is supported on Summit, the performance is indicated by the green bar, which is overall the best. Another thing to consider is the actual runtime performance. Here we compare running TensorFlow from within a container, Singularity container, and outside of the container, which is natively. Same version, same code. The performance are almost exactly the same, which means the overhead of running a framework using a container is neglectable. To summarize, a container can deliver a faster loading time with the same runtime performance. It's a self-contained software stack, a single file, in the case of Singularity container, which is easy to manage and share. But the downside is that building containers on power architecture such as Summit is difficult. And it also lack of flexibility when you try to add library dependencies, etc. As far as I know, the support of a building Singularity container on Summit login node is still in development. Right now, as you heard from Brian and Brad, the IBM WML module is one of our official MLDL software stack. It's built and it's delivered natively. From our experience of running full Summit scale deep learning application, the impact of loading shared library took about a couple of minutes, which is still tolerable. So now you have a software environment set up to do your development. Now let's talk about the parallelization to distribute your deep learning code. So generally, there are two parallel schemes. You heard a lot about data parallel from Brian's talk. In data parallel, basically the same model is replicated on each GPU. And depending how you synchronize the gradients, you could be synchronized there or asynchronized, which will have some implication of model inconsistency and convergence, etc. But the advantage of using data parallel is that it's model agnostic, which means it works for RN, works for CNN, works for GAN, and it generally delivers a very high scaling efficiency. But there are also cases, for example, if your input is too large to fit into a single GPU, not even a batch, or you run into issues of large batch convergence with your data parallel, there's another dimension of parallelization is introduced model parallel. But of course, naively to place each layer of your model onto different device won't work because there's a dependency between different layers. So I will talk about two frameworks from Google. One is called gpipe, the other is Mesh TensorFlow. So in gpipe, it basically divides the batch into micro batch and the pipelining the execution so you can have overlap between different layers. But as you can see from the diagram, the scaling efficiency is not that high. From a small test, we see around 50%. And it doesn't solve the large batch convergence issue because it only divides your batch into micro batch. So the batch size is actually exactly the same. But if your input is too large to fit a single GPU, you may consider a gpipe an option. Another framework is Mesh TensorFlow. Typically, the input of your deep neural network follows number of batch, number of channel, and the image height, image width, NCHW. And for data parallel, it's parallelization on the batch dimension, on the n, dimension of n. So Mesh TensorFlow basically generalizes that. It defines a device mesh and also parallelizes your other dimension like C or H or W. So both of these work actually are in development, and we are closely monitoring that, and hopefully we have some concrete example in the near future. And in the following slides, we mainly focus on the data parallel piece, which is model agnostic and deliver a very high scaling efficiency. So before talking about some technical details, I want to share some considerations about the difference in scaling up deep learning and simulation, because my background is actually from simulation. So deep learning is actually a global optimization. So when you do data parallel, when you change scale, when you add more nodes, you actually change solution space, which means the hyperparameters such as batch size, such as learning rate, etc., need to usually be tuned at different scale. And related to the first point is that for data parallel, it's relatively straightforward to get a very high computational flops count, like in terms of image per second or samples per second. But the actual scaling in time to solution, in convergence, in accuracy, is much, much more difficult. The third point is that because those frameworks and already deliver highly optimized code, for deep learning applications, usually you can easily achieve very high per node flops. It makes deep learning code become communication or I/O bound at a relative small node count. So it requires a lot of considerations in tuning communication and I/O pipelining to achieve a good scaling. So let's talk about a typical training flow chart. Because when we talk about distributed deep learning, we mainly mean distributed training. Generally for inferencing, it's embarrassingly parallel. So for a typical training flow chart, we read an input. We want to cast to 5016 if at all possible, because it's volatile. We want to take advantage of tensor core. We do forward propagation, cast back, calculate loss, then do backward propagation, calculate the weight gradients. If you have data parallel, it means we have many replica of those gradients, then you do a or reduce before you update the weights for each replica. So the communication only happens during the backward propagation before you update the weights. So in terms of data parallel, as you can see, the communication pattern is actually rather straightforward. It's a one or reduce collective call. So you heard about communication libraries, DDL, NICO, and to put them into perspective, this diagram basically shows in terms of scope and flexibility and in terms of scaling performance, what about the choice of those communication libraries on Summit. So MPI obviously delivers the most, it's most flexible because it has all the communication APIs you need. And the NICO right now implement mostly a subset of MPI, mostly collectives. And the Horvath is built on top of NICO and MPI. DDL can be run as one of the backend for Horvath. Also, what's not mentioned before is the framework also provides built-in distribution support, such as PyTorch has torch distributed, TensorFlow has a distributed strategy. They are narrow in scope because they support for particular framework, but they can run on top of NICO, which is actually quite high performance. On Summit, we noticed that NICO, as you see from previous talk, the NICO significantly outperforms Spectral MPI, which is what we recommend to use as a communication layer for deep learning applications. And Horvath delivered an extra performance boost because it did a better job in overlapping communication and computation. A few words about Horvath, because as you heard, a tool of the extra scale deep learning projects I talked about before using Horvath as the communication backend. So Horvath you can consider as a mini MPI for distributed deep learning. It's on top of NICO and MPI. it can be used for popular frameworks. The key innovation is that it introduced the so-called tensor queue. The tensor queue, which is controlled by two key parameters, a fusion buffer and a time cycle, which controls which basically aggregate your or reduce calls and overlap the compute and communication to deliver a better performance. So now let's talk about actual coding part for distributing your deep learning code on Summit. This is in terms of PyTorch. Let's say you want to use PyTorch built-in distribution support called Torch Distributed. It supports both NICO and MPI backend. So to use that, the general first step is always to do initialization, to initialize your communication group. If you want to use MPI backend, it's actually quite straightforward. There's already an API call called the init process group in PyTorch Distributed. To call that initial process group, all you need to provide is the word size, the communication word size, and the rank of your particular process. All of that can be grabbed from environment. If you launch your code with JSRun, those OMP communicate word size and rank are already set because JSRun, the Spectrum MPI is a variant of OpenMPI, right? So if you want to use NICO backend, there are several ways to initialize the communicator. I would recommend to just by setting the environment variable, master address, master port, work site, and rank. Basically, it's similar to MPI initialization. You just grab those environment variable either from your host file and set up, let's say, head compute node as your master and define and grab the word size and rank and follow a call with init process group. Then you have your NICO communicator initialized under the hood by Torch Distributed. By the way, all those PyTorch and TensorFlow examples are available on this open repo we put together, which you can play with after the seminar. So if you remember, we talked about a typical training workflow. The communication actually happens during the backwards propagation before you update the weights, right? So after you initialize your communicator, all you need to do is to call the dist or reduce after a backward propagation, and then before your optimizer actually update your weights. Then now you have now you basically distribute a PyTorch code with Torch Distributed with NICO or MPI backend. You heard from Brian about using Horvath. Horvath supports PyTorch as well. So the nice thing about Horvath is that it took care of the communicator initializer for you. You just call horvath.init, which will set up the corresponding communicator for you. All you need to do is ping the GPU to your local rank, wrap around your optimizer with Horvath distributed optimizer, which will take care of all reduce call under the hood. So DDL can be used as a backend of Horvath. If you are already using Horvath, you can switch to DDL backend without code change. Now let's talk about TensorFlow. So in TensorFlow, there are built-in support for data parallel. We recommend you to use, for single node, it's called mirrored strategy. For multi-node, it's called multi-worker mirror strategy. Also, in fact, PyTorch has such wrapper as well. It's called data parallel or distributed data parallel. In fact, if you set up the same communicator as you saw before for Torch Distributed, you can just wrap around your model with distributed data parallel. It will take care of the all reduce for you. So all of those built-in support are very easy to use, and it comes with framework support. So it works with your existing TensorFlow and PyTorch code, and it's already quite high performant because it can use Nico as a backend. The only thing is that it's less flexible. Comparing using data parallel or distributed data parallel for PyTorch, comparing to torch distributed, those wrapper like data parallel or distributed data parallel is only for data parallel type of parallelization scheme. Let's say you want to develop your new algorithm, or you want to divide your communicator into sub-communicator that currently is not supported for this wrapper, but you can still do that with torch distributed backend. Now let's see an example for how to set up the multi-worker mirrored strategy with TensorFlow. I will skip for single node because if you set a multi-worker mirror strategy, obviously it still works for a single node. The key point here is to set up the tfconfig environment variable. The tfconfig follows a JSON format if you see the bottom lines. It basically needs to specify your cluster and your task. Within the cluster, because we are do a collective communication, not a parameter server, all of the worker node will be, node type will be worker, and then you just need to specify a compute node list for that worker. And for the task, it's all worker. You only need to specify the index, which is the rank of your current process. All of those information can be simply grabbed from a host file or environment variable by simple passing them. You can construct a tfconfig environment variable. And the multi-worker mirrored strategy by TensorFlow will construct the communicator for you under the hood. So another good thing about distributed strategy for TensorFlow is that if you are already using TF estimator, the support of to distribute your code is rather straightforward. All you need to do is to, in your TF estimator, run config to add the distribute strategy as the train distribute parameter. The distribute strategy can be get from TF multi-worker mirror strategy, in which you can specify the communication layer to be Nico. So that's it. Now your code written in TF estimator can run distributedly in a data parallel way. Okay, say your code is distributed. Before you run wild and running large-scale distributed deep learning on Summit, I want to know that always checkpointing. So it's the same requirement for simulation code. In fact, for deep learning, it's actually easier and cheaper to do checkpointing. For example, I know some simulation code the checkpoint file can be terabytes, while for deep learning, the typical checkpoint file is just a couple of GB or less. Because for data parallel, the checkpoints, as you remember, each device has the same replica of the model. So essentially, you just need using a single rank to do the checkpointing. In the syntax of PyTorch and Horvath, you specify, you define a rank, let's say rank 0, to save model and optimizer, then call the torch.save API, that's your checkpoint. In terms of loading checkpoint, again, you use a single rank to load your model, load your optimizer, then broadcast those parameters. As you can see, because it's data parallel, you actually can run at a different scale with the same checkpoint. Because let's say you checkpoint at 16 nodes, then you can save the checkpoint form and restart at 32. as well. It should work as well. Okay, now let's assume you have your deep learning code distributed. It's time to talk about the performance tuning of your distributed deep learning code. There are several knobs on Summit that you can consider. So generally, when we talk about performance tuning, we mean finding a sweet spot between compute, I/O, and communication that you have perfect scale, right? In terms of compute, you know, the cuDNN, which is the working horse for both TensorFlow and PyTorch. That's what you want to focus on. For I/O, you need mostly consider I/O pipelining and the different input format like TF-Record, LMDB, HDF5, etc. And in terms of communication, there are communication libraries like MPI, Nico, however, available on Summit right now. So we recommend you generally follow the first step is to tune your compute on a single node with synthetic data. This way, you can isolate the impact of I/O and communication and get a baseline of your GPU processing speed for your model and your input dimension. So with that GPU processing speed as a baseline, then you can tune your I/O on node local NVMe with input pipelining, different input format, so you understand what's the impact of adding I/O. Once the compute and I/O are tuned, then you can tune the communication at scale with different communication libraries. In terms of compute, as I mentioned before, use Tensor Core. I mean, you know, the Volta deliver a single precision performance is 15 teraflops. In half precision, it suddenly jumped to 120 teraflops because of Tensor Core. So on average, we see that a deep learning application can get a 2 to 4x speed up just by using Tensor Core, which means use half precision if at all possible in your PyTorch or TensorFlow code. In PyTorch, NVIDIA has this Apex library which help you to try different precisions. And by the way, Apex is also part of library delivered by the Watson machine learning module, so you don't need to install or build it. In terms of TensorFlow, there are automated mixed precision support just by turning on the environment variable. So you can try different to see the results for your half precision. To verify the performance on Tensor Core, you can turn the cuDNN Tensor Core operation on and off by setting the environment variable, or look at the NVProf performance to look at your Tensor Core utilization. Another point about compute is to use XLA. XLA is accelerated linear algebra compiler because, as you know, by default, TensorFlow is shipped with pre-compiled binaries for those operations on GPUs. By enable XLA, it will compile model-specific optimization for your particular code. We observe a 1.5x speedup for ResNet 50 just by turning on XLA. Since the cuDNN is the actual working horse behind the scene, it's also important to tune the cuDNN algorithms. For example, for convolution alone, there are, I think, over 10 implementations now. There are FFT-based, germ-based, etc. You can turn the cuDNN auto-tuner. Let's say pick the best algorithm for your code. Of course, if you know your kernel, you can also handpick best scheduling policy for choice of algorithm, depending on your kernel parameters. We actually benchmark different kernels for convolutional type or RN type of kernel and observe the performance difference on Volta comparing to, this is the speed up over P100. So let's say for convolutional kernel, you have different input parameter, let's say filter size, number of filters, kernel size, etc. You can get up to 11x or 1.2x depending on your input kernel parameters. The most important parameter for CNN kernel is the kernel size and number of kernels, and for RN, it's batch size and time steps, etc. This is just keep you aware of the different speed you can get depending on your kernels. Now let's assume your compute is tuned, you're highly tuned. Now you have a target number, which is your GPU processing speed. In terms of ResNet 54 ImageNet, the GPU processing speed at full summit scale is around 20 terabytes per second. Now it's time to tune I/O. As you may know, the GPFS provides an aggregate reading speed of 2.5 terabytes per second. If you compare with the target GPU processing speed, you know that it cannot keep up with the GPU processing speed. The GPU will be waiting for data most of the time. So it's essential to use local NVMe, which provides an aggregated reading speed of 27 terabytes per second. Another aspect to consider is different input format. Here we consider TF record, HDF5, and RMDB. So TensorFlow supports both TF record and RMDB format, and RMDB works for PyTorch as well. And HDF5 is most used scientific data format. So we consider different reading bandwidth for different format for your input data, same input data. Because the I/O operation are mostly happen on CPUs, we also consider different hardware threading, SMT level 1 to level 4 for 3 input data format. In all cases, what we found is RMDB provides the best reading bandwidth. As I mentioned, because most I/O operation happens on CPU, it's important to set a correct CPU affinity binding. You can do that using NUMA control and OMP place. This script is available in the repo as well. So by doing that, you can get extra 10%. But most importantly is use pre-processing pipelining, which is extensively documented in the framework's official documentation. Please follow that and consider using staging, prefetching, parallel interleaving, which is essential to deliver a good I/O performance. Assume your I/O and compute are tuned. Now it's time to tune your application at scale for communication. As we talked about earlier, there are several communication libraries you can choose on Summit, and we compare them for TensorFlow and PyTorch. If you are using Torch distributed with MPI backend, the performance is as indicated by the blue curve. And if you switch to Nico backend, you see a sudden jump in the performance processing speed. If you're using Harvard on top of that, which is indicated by the green curve, there's an extra performance boost. The same thing holds for TensorFlow as well. We compare the Harvard performance with multi-worker mirrored strategy. So the scaling efficiency are comparable, but there's a extra performance boost on Harvard at all scale because Harvard overlapped the compute with communication better. So we recommend you use Harvard as communication library with Nico backend. And there's also 2 key tuning parameters, tuning knobs for Harvard. One is the cycle time, which determines how often you do this or reduce calls. One is fusion threshold, which is determining a fusion buffer, which is set an upper bound for your communication message size. By the way, Harvard also provides an auto-tuner with a Bayesian-based auto-tuning. You can set it on with the environment variable Harvard auto-tune. Then it will find the best cycle time and the fusion threshold for your code. It is recommended you do auto-tuning at a different scale as well. Because, as you showed earlier, Nico significantly outperformed MPI on Summit. We recommend you to turn off the hierarchical or reduce and hierarchical OR gather, which basically use MPI as a communication layer across nodes. If you want to look at the actual message size for all your OR reduce, you can do that by setting up the Nico debugging environment variable, which will print out all the details for your OR reduce. In the bar chart shown here is a comparison of the message histogram for the default setting for Harvard, and the auto-tune picked best message size. Just to give you a feeling about what message size works best. I also briefly mention two modifications we introduced to Harvard during this full-scale material science run. So the first is called bit or reduce. When we scale our code using Harvard on Summit, one thing we immediately notice is that the negotiation phase, this is from the Harvard timeline trace, which is a tracing profiling tool provided with Harvard. And you can notice that the negotiation or reduce actually took much longer, 10 times longer than the actual or reduce call. That's because originally Harvard used centralized coordination. The coordination is needed in Harvard because, as I mentioned, it aggregates the or reduce and overlap between compute and communication. So there's a negotiation between different rank to see which tensor is ready to be or reduced at this cycle. But this original implementation of coordination used a centralized scheme, which involve MPI gather and the broadcast. That obviously won't scale at scale, large scale. So we introduced the bit or reduce, basically replace that with another collective call. We use a bit vector to mark which tensor are ready to be or reduced, 1 or 0. Then all coordination can be done with a single bit or reduce call. By doing that, if you look at the time trace chart again, now the or reduce most of the time are spending on the actual communication. The negotiation phase is much shorter now. Another thing, by the way, the bit or reduce bit is already in the main Harvard distribution, so you are already using it if you're using latest Harvard. Another improvement we call grouping is by the consideration that, let's say your deep learning code is highly latency bound. Let's say your per step, one batch processing took less than, let's say, 100 milliseconds. In that case, you want to use a very short cycle time because you won't have a low latency communication. But by setting a very short cycle time, you defeat the purpose of aggregate those tensor for communication. We introduce a grouping which basically map the communication group to your network topology. Say an ideal case, a sample case could be, we want to all reduce layer by layer, which will provide a better overlap between compute and communication. By doing these two strategies, overall there are 8 times speed up for our code, which is a tiramisu network on a much larger input data. In that case, the overall scaling efficiency indicated by the red lines above 95% up to 1,000 Summit nodes. So if you are using Harvard with the latest master, you're supposed to get the scaling performance as indicated by the black line. which is with BitOro tools incorporated. To give you a feeling over a popular benchmark ImageNet training for the TFCM benchmark on Summit, you can expect a scaling efficiency about 87% up to 1,000 Summit nodes. If you look at the batch size, so it's actually, the total effect batch size is actually quite large. We process the entire ImageNet dataset, which is about 1.5 million images, and iterates through it 3 times in a single batch at 1024 Summit nodes. As you expected, obviously that won't converge. This is just to show you a processing speed, the highly scalable data parallel scheme. In practice, that large batch size won't scale, as you heard from previous talk. For ImageNet data on ResNet 50, the larger, when you effective batch size is bigger than 16K or 32K, you see a significant drop in the model accuracy. There's one paper argues that that's because when you have a large batch size, your estimation of the gradients is much more accurate, which means your movement in the loss landscape is much more smooth. The loss of randomness could result you get easily trapped into local minimum and result a loss of accuracy. There are ways to alleviate that. One popular algorithm is called layer-wise adaptive rate learning, LARS, which is incorporated in TensorFlow, I think also PyTorch. By using that, in terms of scaling time to solution, you can expect ImageNet training with 16 Summit nodes in about half an hour. If you use 64 Summit nodes, you can train ImageNet on Summit in around 10 minutes. So this example is also available in the repo. You can play around to see what's the best training time you got. But generally, when your training time is down to about 10 minutes, it's generally acceptable because you're going to spend a lot of effort to go beyond a certain large batch size limit. Now let's assume you have your distributed deep learning code highly tuned. Now it's time to tune your model to find a better accuracy with hyperparameter search. So there are several hyperparameter search tools. Here I just use one of them, open source scalable hyperparameter tuning library called RayTune from Berkeley as an example. So it supports both PyTorch and TensorFlow and some other framework as well. So RayTune is based on the Redis cluster. Redis cluster is a typical socket-based master worker setup, just like Spark. Because in hyperparameter tuning, the communication is not the bottleneck. So usually using Redis cluster for this purpose won't be a bottleneck in terms of scaling. Because you basically mostly running different experiments on different Summit nodes, and they communicate occasionally. Here is a script to set up the Redis cluster on Summit. It's because of the cluster nature of Summit, it's naively just use SSH to start up the head node service, master service, and start up the worker service on each node. And then you have your Redis cluster stand up. In your code, to use RayTune, you just need to wrap around your model and your training with RayTune trainable class. Basically override 2 functions, setup and train. In the setup, you define how your model is built, and you define which optimizer to use. In the train, you define which procedure to use as a training of your model. One key parameter is the config. Config is obviously related to the hyperparameter you could fit in for this particular instance. In this case, we're gonna read in the DAS, which is the ResNet DAS, for example, and the learning rate, ARR, and the weight decay as a training parameter. After you wrap around your model with trainable class, you call the trainable class with such as follow. First, you initialize your RAIN cluster to connect to the Redis cluster you just initiated. Provide the address and port number. Then you start up your job scheduler. In this case, I use population-based training, which is developed by DeepMind. Then you call your experiment with run experiment API and specify your experiment setup with train spec. Inside the train spec, you point to where is your trainable class. In this case, let's say Cypher10 data. What is the resource for your each experiment? In this case, we use all 6 nodes, all the GCPU's cores for the single experiment parameter. You define your stop criterion. Let's say, mean accuracy 90% or train iteration 50 epochs, whichever comes first. Then you define your search space. Let's say I want to do a grid search on the learning rate from a range. I want to search for weight decay from a sample from a sampling. And I want to try different ResNet model. Let's say ResNet 20, ResNet 32, up to ResNet 50 in the DAS parameter. So then Ray2 will take care of all the job handling, all the job initialization for you. One good thing about Ray2 is that it integrates nicely with TensorBoard. So you can visualize your hyperparameter search as it's running. It supports both TensorFlow and PyTorch. And for this snapshot, it's for population-based training. A few words about population-based training. In this algorithm, it basically starts from random initialization of different workers. And then periodically, in this plot, is every 10 epochs, those low performers will mutate parameters to those closer to high performers. That's where you see those sudden jumps every 10 epochs. It will jump of accuracy because more workers are searching in the parameter space that provides promising answers for you. So all of those can happen interactively while you're training your job. Okay, now we covered the entire training process life cycle of develop your distributed deep learning. I would like also say a few words about model deployment. This is a particular case for using TensorFlow C++ binding for inferencing. A typical use case of this is for surrogate modeling. Say you train your got your data from simulation, then you train your data with a Python interface, train offline. You save your model checkpoint, which generally follow this format. It has a .meta file, which is a protobuffer file with your TensorFlow graph, and the binary file .data.index, which contain your model weights. You can optimize your checkpoint, of course, with these tools. But once you have checkpoint, you can deploy the model with your simulation code. In this case, I assume your simulation code is C++ as well. Then you can compile your model and your simulation code into a single C++ binary and do model inference as a surrogate, replacing part of your simulation workflow. So a typical C++ syntax to load your model is you create a TF session, follow a C++ syntax, you ping to the local rank as you did do for a Python case as well. You create your session, then you load your TF graph file, which is the .meta file you saw previously. Then you load your checkpoint by running the section on your checkpoint file. So I won't go into detail of those, but typically those procedures are available from official documentation as well. I want to say show a few details about compiling. By the way, inside the IBM WML module, the C++ binding for TensorFlow and PyTorch are available. So you can build your C++ backend using TensorFlow and PyTorch with IBM WML module. Just remember to use the latest version of GCC. And if you're using TensorFlow, the header file and library file can be found using tf.systemconfig, which will find the correct path for you. Then after setting the head path and the library path, you can compile in your code along with your simulation code. So to conclude, we cover an end-to-end development cycle of a typical deep learning application on Summit to show that Summit is ideal for deep learning applications. And to have some baseline, for ImageNet training with ResNet 50, you can expect 87% scaling efficiency up to 1,000 Summit nodes. If you are using more expensive model like UNet with larger input data, bigger than the typical ImageNet data, 224 to 24 by 3, you can expect a better scaling efficiency than 87%. For example, for our material science project, the full Summit scaling efficiency for data parallel is 93%. But of course, there is the issue with large data parallel jobs because of the convergence. You may need to consider hybrid parallel, such as model parallel, if you want to utilize full Summit parallelism. Another aspect of parallelism is also combining your data parallel with hyperparameter search as such. So the PyTorch and TensorFlow example are available in this open repo. Follow the link. And for more details, there's a conference paper we present at SC19. And of course, there are a lot of good resources from official documentation. Please take a look in the official documentation for the data best practice and distributed training in TensorFlow and PyTorch. And some people ask about Harvard, and the Harvard repo already provides a lot of examples. Most of the example can be run on Summit without change. And also there are RayTune documentation as well. That's the end of my talk. Yep, thank you for your attention.
Right, thank you very much, Junqi. Does anyone have any questions for Junqi? Anyone in the room have questions? Hand this mic off here.
You said that the number of degrees of freedom usually expands when you increase the parallelism. Can you give us a sense of like how much the number of degrees of freedom increases? Is it just linear with number of nodes?
You mean for data parallel, the large batch convergence issue?
Right.
So right now for ResNet 50, the largest batch size is around 32K. So typically for ImageNet, 1 Volta GPU can hold 256 if you use high precision. So you can do the math, 32K divided by 256. That's the largest scale you should consider for ImageNet training or for ResNet 50. So, and we do notice that this problem, large batch problem, is generic enough. For scientific applications, we do see this limit as well, usually around 20K or 16K. So if you want to limit your batch size around 10K, it should be get a good performance in terms of processing speed and without loss of accuracy.
Is it common then to, when you're checking for accuracy, and also scaling at the same time to run at different scales so that you can see if a smaller number of degrees of freedom gives you better accuracy? How do you work that in? I mean, is there like usually a cutoff where you say this is too many degrees of freedom?
Usually, yes, when you do the large-scale dispute training, you always train at the modic scale first, because that's the thing for deep learning. The difference with simulation is that the parameter needs to be tuned at different scale, at each scale. So you might want to try with the moderate scale first and tuning your code.
Thanks.
Sure.
Right, anyone have any additional questions for Junqi right now?
A question probably also to tech support. That's related to the deployment part of the talk. The container builder was kind of advertised to be coming soon on Summit. What's the status of that? When should we expect it, or should we expect it at all?
You're asking about the Singularity container?
Yes, because right now it's all great, but regular user cannot really build a container with his or her own recipes. You can take Docker from IBM, Docker Hub, and play with that, going to hybrid scheme. Let's say container has TensorFlow, but it doesn't have some Python modules that are required by my model, and you store them somewhere locally, and there's a go along this way. It's doable, but container builder would be an ultimate solution in the user space for Singularity containers with deep learning or other models or simulations on Summit.
Right. Because of Summit's power architecture, most x86 container out there won't work on Summit. And right now, as far as I know, we are working with Scilab to build a container builder so that users can build their own containers on the Summit login node. And but that part of work is still in development. Right now, if you had root access to a power architecture, essentially you can build your container and bring to Summit, because Summit can run Singularity containers.
Right. The point is that power architecture usually hard to come by, not to mention root for regular scientists.
That's true.
Okay, so
there is no ETA for that container builder. I mean, because it's been promised for a year, more than a year right now. I'm just curious, is it's dead end or there is a light at the end of the tunnel?
It's been delayed a couple of times, as far as I know, and the point of contact, I think, is Jack Morrison. Am I right, Tom?
Yeah, I think that if you were to submit a user support ticket on that, that's who would end up talking to you about it, is Jack. So that's probably the right way to go about asking that question. But I don't have an ETA beyond that it's being worked on.
Okay, thanks.
There is a question in the chat here asking about the most important things to take care of when scaling Horvath from DGX to Summit on, say, 24 GPUs. Is there any advice you can give for this user?
Sure. So the first thing consider when you tuning Horvath is to use the Horvath auto tuner as shown on the slides. The key tuning knob for Horvath is the cycle time and the fusion threshold. So by setting up the auto tuner, when you run your code, it will search different combinations of cycle time and the fusion threshold and find one that work best at the scale for your code. But of course, you can look at more debugging information of the actual message size, etc. And if your application has a high latency requirement. For example, so if your training per step time is very short, less than 100 milliseconds, you may consider the grouping strategy, which is not yet merged into the Hover mainstream, but on as a pull request there. But I would suggest you start with the Hover Auto-Tune, which generally find very good parameters for you to scale.
Are there any other questions, Junshi? Or for anyone, I guess we could open this up for additional questions. Right, so it looks like this is a question we were going to come back to that's been repeated here. Someone has seen issues, well, you can probably read that as well, but somebody has seen issues with PyTorch distributed data parallel deadlocking with Nickel on non-Summit systems. Has there been any indication of that on Summit?
I haven't seen any of that in particular. We've seen some issues with MPI and PyTorch, but not necessarily with Nickel.
Okay, so there was actually another question that was asked. If IBM Machine Learning Toolkit already includes Nickel utilities, why do I need to be aware of low-level Nickel? And then following that, does IBM Machine Learning Toolkit provide Nickel primitives for users at runtime? I guess that's a IBM question.
We provide the entire Nickel package, Nickel library. So you have access to the whole Nickel library, so you can call any kind of Nickel function you want. I'm sorry, there's like a really bad echo. I don't know if you guys are hearing that also, but making it a little hard. Okay, cool, thanks. So you have access to the Nickel library. You won't have to rebuild that from source. You have that in your Conda environment. You also will have all the frameworks that have already been built against Nickel, so TensorFlow or PyTorch or Orva, they've all been built against Nickel. So you'll be able to use it that way as well. For a lot of your uses, you probably don't need to be aware of Nickel that much. If you're just using Horovod, you won't really notice anything about Nickel unless you need to start setting some environment variables for tuning, but other than that, it'll kind of just work. And if you're using the PyTorch backend for Nickel, again, it'll just be there and kind of work. So until you start getting into kind of some tuning areas, you don't really need to be aware of it all that much, other than that it's there and should be performing well.
Okay, thanks. Are there any other questions from anyone, remotely or in person? Okay, well, if that's all the questions, then I'd like to go ahead and thank all of our speakers right now for great presentations. Thank you. So the presentations have been asked several times in the chat. The presentations and the recording of this will be available on the event page where you registered for this event. So you'll be able to go there. The presentation should be out soon in the next couple days. The slides, that is, the recording might take a little bit of time for some video editing, but they'll both be available there.